Okay, so we are now into section 2, chapter 3. This is logarithms. Actually, logarithms and exponentials. And, those are, we call those inverse functions because f of g of x and g of f of x equals x. So, first thing is just to show how you go from logarithmic functions to equivalent exponential functions. And this is with numbers with variables. So our first problem is log to the base 3 of 81 equals 4. So logarithms is saying, what power do I need to raise 3 to get 81? The answer is 4. So the equivalent expression is 3 to the 4th power equals 81. What number do I need to raise the base to, which is 3, to get 81? 3 to the 4th. So that's how that one works. Okay, the next one is logarithm to the base 10 of 1000 equals -3. So the base is 10, the exponent is -3, the answer is 1000. Actually, it's not 1000, 1000. And that comes from, 10 to the minus 3 powers is 1 over 10 to the 3rd power, which is 1 over 10 times 10 times 10, which is 10 times 10 is 100 times 10 is 1000. Number 6. Log to the base 16 of 8 is 3/4. So again, the base is 16. So 16 to the 3/4 power is equal to 8. So this part is the base. This would be the exponent needed to get the answer. And if you think about what that is, it's 6. The 4th root of 16 raised, the whole thing raised to the 3rd power. So the 4th root of 16 is 2, because 2 times 2 times 2 times 2 is 16. And so then you get 2 cubed, which is 2 times 2 times 2, which is 8. So that's why that works out. Okay, number 11, another group. Write the exponential expression in logarithmic form. So that's going the other direction. So what do we have? We have 81 to the 1/4 power is 3. So the base is 81. So we'd say the log to the base 81. And the answer, the argument of the log function is 3. And the answer is 1/4. What power do we need to raise 81 to get 3? And what we're doing here is, how could we, to the 4th power is the 4th root of something. So what number multiplied by itself 4 times gives me 81? Well, the answer is 3. Okay, 13. 6 to the minus 2 power is equal to 1/36. Again, the base of the log function is the base of the exponent. The answer is, the argument of the log function is 1/36, and the answer is -2. So when we look at this, it says, what number do we raise 6 to get 1/36? Well, the answer would be -2 power, because 6 to the -2 power is 1 over 6 to the squared, and 6 squared is 36. Okay, one more more in this section, which is one more, two more, one more. So we have e to the 1/2 equals 1.648 dot dot dot. Okay. This is my base, so I say log to the base e of 1.6487 equals 1/2. What number do I need to raise e to get 1.684? Raise it to the 1/2 power. And we call log to the base e, we call that the natural log. So you'd say the natural log of 1.6487, some more digits, equals 1/2. Okay, 21. The value of the function at the indicated value of x without using a calculator. Okay, so we have f of x equals log to the base 7 of x, where x is equal to 1. So that says f of 1 is equal to log to the base 7 of 1. So the question is, what number do I raise 7 to get 1? Well, any number raised to the 0 power equals 0. So anytime you have a logarithm of 1, doesn't matter what base it is, the answer is always 0. So log to the base 10 of 1 is 0. Log to the base 276 of 1 is 0. And if you plot the logarithm of functions, you'll always see that they go through x equals 0, x equals 1, y equals 0. Okay, 25. G of x equals log base a of x. X is equal to a squared. So g of a squared is log to the base a of a squared. So the question is, what number do I need to raise a to get a squared? Well, the answer is 2. Now another way we'll find out later, I think, maybe it's in this section, but one thing you can do with properties of logarithms is say that you can take the exponent out. So you'd have log to the base a of a. Well, the log to the base of anything, the same thing, is going to be 1. So you get 2 times 1, which is 2. So there's two ways of thinking about use properties of logarithms. You can also just think about what they're asking. A is the base. Raised to what power? That's what you're trying to figure out, is a squared. Okay, 33 through 38. So those are those graphs that match up. So again, you have to think about what's going on here. The parent function for the logarithm looks like this. It comes up from negative infinity, goes through x equals 1, y equals 0, and then kind of loops over here. So that's the log of something. I'm going to say second power just for argument of x. Log to base 2 of x looks something like that. Okay. Now if you did log to the base 2 of negative x, again, what the negative sign inside does is it reflects it across the y-axis. So your logarithm is going to look something like this for that one. And then if you do negative log base 2 of x, then you reflect across the x-axis. So this thing comes down like this, like that. And then the shifts are just normal. If I add something here, then it'll shift vertically. If I have something in here into the argument, then it shifts horizontally. So let's just start off here with 33. So you have f of x equals log to the base 3. I guess these are all log to the base 3. So it's going to look something like that one over there, approximately, of x plus 2. So the only difference is you're going to shift up 2 units. So we need one that looks like this, but shifted up. So instead of crossing the x-axis here, it's going to have a value of, at x equals 1, it's going to have a value of y equals 2 instead. So let's look for something that looks like that. So that rules out pretty much all of them except C and E. And the only one that's shifted up is going to be C. So that's that one. Because we're going to, anyway, so the parent function look like this, and all we're doing is shifting it up like that. Okay, 34 is f of x equals negative log of base 3 of x. So we said when you have the negative sign out here, then what that does is it reflects it around the x-axis. So it's going to have to be one like this. It's going to have to be fully to the right of the x-axis. So let's look for ones that have this shape, the green shape. The only two are D and F. And D goes to the left, shifts over this way. So that's not it. So it must be F. Okay, 35 is f of x equals negative log of x plus 2. So this negative sign, just like the previous one, means it's going to be reflected like this, but because of the argument here is not just x, you're going to shift. So here we said, we didn't write it down, but reflect across x-axis. We're going to do the same thing here. We're going to reflect across the x-axis because of the negative sign. And we're going to shift to the left. So we always have x minus h. So x would have to be negative 2. So you'd have negative and negative, give you positive. So shift to the left 2. Okay, so well, the only two that had this property of looking like the green one were the one we just chose, and the other one, which was D, which is shifted to the left 2 units. So this one is D. Okay, 36. You've got f of x equals log to the base 3 of x minus 1. So the only transformation we have is there, and we're moving to the right. Shift right 1 unit. So we take this one and we shift it. So we look for one that's this shape. So that leaves us with just C and E. And you can see we've already actually used C, but E is shifted to the right 1 unit. So that one matches up. So that's E. (37) f of x equals log to the base 3 of 1 minus x. So we just have to factor out the negative sign within the argument. We can't ever factor it out completely. So you have negative times x minus 1. So instead of 1 minus x, it's negative quantity x minus 1. This means shift right 1. And this means reflect y-axis. So if we come over here, the red curve is the reflect, and then you shift to the right. So we should have one that has this general shape, which is either there's actually only one that has that shape, which is b, and you'll notice that it has been shifted, because normally it would go through -1, but it's shifted to the right, so it goes through 0. So this is b, and then 38 is f of x equals negative log to the base 3 of negative x. So we got negative and a negative. So what happens here is we reflect across from this one, this negative is across the y-axis, and this second negative here reflects across x-axis. And it doesn't matter which order you do it in, because if you think about this, let me get blue. So here's the original function reflected across the x-axis. Then if you reflect the green across the y-axis, it's going to look something like that. Now, if you do it the other way, if you first take the parent function, the black line, you reflect across the y-axis, which is the red curve, and then you reflect across the x-axis, gives you the same blue curve. So it doesn't matter. So we look for one that has this kind of shape to it, which is, there's only one that looks like that, which is A. And it was the only one that we had left anyway. So that works out good. Process of elimination, as well as just using the transformation information. Okay, 41. The next bunch, find the domain, the x-intercept, and the vertical asymptotes of the logarithmic function. Sketch its graph. Okay, so we have y equals negative log to the base 3 of x plus 2. So I think what they want us to use these transformations. And then once we have that, we can do it analytically and graphically. Let's do it. So here's my parent function. It looks kind of like that. And this negative means that it's reflected across the y-axis, so it's going to go like that. And then it's going to be shifted up 2 units. So what happens is this gets moved up 2 units, but it doesn't get shifted in the x direction. So it's still going to have the same asymptote. It just approaches it differently. So the domain. The domain is the possible x values. And you can see that it's off to the left here. So it means that it's from negative infinity to 0, but not including 0. The next thing you're asking for is the x-intercept. Now the x-intercept is not going to be 1, it's going to be somewhere between 0 and 1, so that one you actually have to solve this thing. So you'll have, you set y equal to 0 in the original equation, so you get 0 is equal to minus log to the base 3 of x plus 2. And then we get negative 2 is equal to negative log to the base 3 of x, and divide by negative 1, multiply by negative 1, so you get log to the base 3 of x is equal to 2. So how are we going to solve that? Well, the inverse properties of logarithms and exponential functions, I think that's in this section. What you do is you'd say, I'm going to raise both these sides to the 3 power. 3 to the natural log of 3 is just x, and here you get 3 so that's not what I expected, because the way I thought this thing was shifting, that I would get it somewhere between these two values, which is not what's going to happen. So what did I do wrong? Okay, I'm just going to pause for a second. I'm not sure what I got to think about this. Okay, so I just realized what I did wrong. I reflected this the wrong direction, didn't I? This negative sign means reflection across the x-axis. So it looks like this, like that, kind of like that. And so then what happens is it gets shifted up to. So then it looks like something like this. So it crosses somewhere else out here, which turns out to be 9. So the answer is 9. So that's the x value for y equals 0. And the domain is wrong. So it's actually from 0 to infinity. Can't equal 0. And the vertical asymptote is x equals 0 still. Okay, next one. 43. So we have f of x equals minus log to the base 6 of x plus 2. So in this case, we have a shift in the x direction, and we still have a reflection across the x-axis. So let's kind of sketch what this thing looks like. So our parent function, natural log of x, looks something like that. So when we reflect across the x-axis due to that, then we have something that goes that direction. And then finally, if we shift 2 units, we're going to shift the asymptote. And we shift everything 2 units. So instead of intersecting here, we're going to intersect there. We're going to have a vertical asymptote at this point. And it's just going to come down this vertical asymptote through here, like that, and over there. So, domain. So we can't go to the left of this. So the domain is going to be from 2 to infinity. The x-intercept, the intercept doesn't change except it shifts from x equals 1 to x equals 3. And the vertical asymptote is the boundary here, the domain. So it's x equals 2. So that's the line. This red line is x equals 2. There's the intercept, the domain, is everything to the right of that thing. Okay, 45. So we get y is equal to log base 10 of x divided by 5. So this is one of those shrinking, stretching things. So it's not going to change the general things about the asymptote and the, but what is going to happen is that the log to the base 10 of 1 is 0. So the x-intercept is going to be, instead of be 1, it's going to be 5. Because when x equals 5, the argument is 1. And therefore the value, log to the base 10 of 1, is 0. But it still has this x equals 0 asymptote vertical asymptote. So it kind of comes down through like that. So it's getting stretched out in this direction. Except I'm going the wrong direction here. So let's fix that. So it's not negative x, it's not negative logarithm, so it goes in standard direction for a logarithmic function. It just gets stretched out to that point. So based on that drawing, we can say that the domain is still going to be from x equals 0 to positive infinity. The x-intercept is the point 5, 0. X equals 5, y equals 0. That's what x-intercept is. That's when y equals 0. And then the vertical asymptote is the line x equals 0. I almost wrote 5 in there, but it's 0 because it's always this part of the domain, this edge of the domain. And 47. So we have f of x equals the natural log of x minus 2. So it's just the natural log, which is just like other logarithms. It's just this slope of the thing is different, but what that does is this is going to shift to the right 2 units. So that's going to change the asymptote. It's going to change everything really. But we're going to draw it so we can think about what's going on here. So again, our parent function is going to be something like this. It's going to come up again when x, the natural log of 0 is going to be, the natural log of 1 is 0, so that makes it go right through there, and then it kind of loops around like that. So all we're doing is shifting it to the right 2 units. So instead of intersecting there, it's going to intersect there. That shifting, it also shifts the vertical asymptote. So the intercept shifts, the vertical asymptote shifts, and everything else has the same shape. So it looks something like that. So the domain is going to be x is going to be greater than 2, less than infinity. The x-intercept, instead of being 1, is going to be now 3. So it's x equals 3. And the vertical asymptote and this is x equals 3, y equals 0, so that would be the point 3, 0. The vertical asymptote is x equals 2. So there's your vertical asymptote, x equals 2. Your point of intersection, 3, 0, and your domain is everything to the right of the vertical asymptote. Okay, I think we're into a new section here. Use a graphing utility to graph the function. Be sure to use an appropriate viewing window. Okay. So we have f of x equals log to the base 10 of x minus 1. So this is what we should expect. Here's the parent function. Again, it still goes through x equals 1, y equals 0. And then it goes like that. This is going to shift it to the right 1 unit, so everything shifts. The vertical asymptote shifts. The point of intersection shifts. So actually, it's going to shift just right to there, and then it'll go like that. Okay. So let's plot this thing. So what do we have? Log to the base n of 10, x minus 1. See if that works or not. Yeah, I don't know. I think that's must be another way of writing logarithm to base 10. Let's go to, if you go to help, where's help? Oh, there's help. Oh, it's the other way around. So that's why it's all messed up. Okay, so it's logarithm of x minus 1 to the base 10. There we go. That should work this time. So there you go. So it still has an x-intercept at x equals 2 instead of x equals 1 because it's shifted 1 unit. The base 10 makes this thing a lot flatter. Okay, 54. So that is f of x equals the natural log of x plus 2. So this is going to shift to the left 2 units instead of the right 1 unit. So our base function looks like, the parent function looks like that. And if I draw a little red thing on top of that, all it's going to do is shift it 1, 2 units to the right, to the left, to the right, to the left. One of those things. Okay, and because it's a natural log, I don't have to put the base, so it's just the natural log of x plus 2. I graph that. We'll just go to standard zoom here. So you can see now the intersection used to be positive 1, now it's negative 1. It's shifted 2 to the left. But otherwise, if I just plot the natural log of x, which is the parent function, it's the same thing. It's just been shifted. Everything's been shifted 2 units to the left. And then the last one in this group, 56, is f of x equals 3 natural log of x minus 1. So this is a vertical. This is up or down. It's negative. So it's down 1. It's going to, so let's just draw this thing out. So here's my parent function. Looks something like that. So if I draw right over top of this with my red pen, and then I move it down 1 unit like that. So it still has the same vertical asymptote. And then what this is going to do, the 3 is going to stretch this thing out. So it should be, it'll still go also this vertical asymptote will change on the red one. So the vertical asymptote will be at x equals 1, so it shouldn't have crossed over there. And then the green is just going to stretch this thing out. So it still has this anchor point here, but it's going to look something like that, and then it's going to go like that. So that's what the number out in front does, is it stretches in the vertical direction. So we're going to, and this was the natural log. So I just do, so I'm going to do kind of the different parts. So you get the natural log of x, then you get the natural log of x minus 1, and you get 3, the natural log of x minus 1. Let me graph that. Okay. And so here's the parent function. Here is the thing moved down 1 unit. Actually, it didn't affect the x. Yeah, we didn't shift in the x direction, so that was my fault. So it shifts down, but it still has the same vertical asymptote. And then the 3 times natural log of x has the same point as natural log of x minus 1, but it then just pulls it out, stretches it out in the vertical direction. And one last problem. So this is a fairly long problem. It says the model t equals 12.542 times the natural log of x divided by x minus 1,000 for x greater than 1,000 approximates the length of a home mortgage of $150,000 at 8% in terms of monthly payments. In the model, T is the length of the mortgage in years and X is the monthly payment in dollars. Use the model to approximate the length of a $150,000 mortgage at 8% when the monthly payment is $1105.65. So they want us to use this graph to approximate what's going on. So I'm going to cheat a little bit and I'm going to do this function that we've got and I'm going to scale it appropriately. So it's going to be 12.542 as the natural log of x divided by x minus 1,000. And I'm going to start at 1,000. And I'm going to go to, how many? They got about 12,000. Actually, let's go to, 12,000. And the y value goes from 0 to 30 years probably. That's good enough. Okay, so there's the function. Now it says use the model to approximate the length of a $150,000 mortgage at 8% when the payment is $1165, and so this is for a $150,000 mortgage. So all we have to really do is we just have to go at around 1,000 and $1,165. So you can see, just zoom in. Okay, so you go at $1,165, which is about 25 years. And if you have a payment of $1,254, what I'm doing is look at the X value, $1,254. It's going to be about right there. That's about 20 years. Now let's see if I can do that. And actually, in this case, we can use the equation, so we don't have to use the graph. So t is equal to 12.542 times the natural log of, and x is the monthly payment, I think. Yep. So we have 1,165 divided by 1,165 minus 1,000. We plug that into our calculator. We get 12.542 times the natural log of $1,100.65, and then you divide by $1,100.65 minus 1,000, and left right parenthesis, another right parenthesis, another right parenthesis, and I get 30 years. Okay, so t is 30 years. That's what we saw off the graph. So okay, so you plug those in, you get 30 years. Okay, now if we do the same thing with the next value, 12, you get 1254.68. 1254.68 divided by 1254.68 minus 1,000. Plug those in the calculator. 19.99998, so it's 20 years. So the point here is, notice the mortgage payment is about $150 more a month, which is about a little over 10% more, but you can cut the number of years that you pay from 30 down to 20. So you try to pay as much as you can on your mortgage so you pay it off sooner and you pay less interest. Okay, approximately the total amount paid over the term of the mortgage with a monthly payment of $11.65. So part B is all you have to do is take your monthly payment, which in the first case was $1,065 per month, and multiply by 12 months times 30 years. And in the second case, take your monthly payment, $1,254.68 per month times 12 months times 20 years. And this gives you the total amount that you paid under these two circumstances. So let's see how much difference there is. So here I have to pay $396,234. And in the second case, I have to pay $301,123. So I can save almost $96,000 or $95,000 by paying off my mortgage in 20 years instead of 30 years. Now that's because the interest rate's pretty high, 8%. If you have a lower interest rate, it makes less difference. Approximate the total interest charge for the monthly payment of $1,065 and for a monthly payment. So the interest, so what you can think about is that the house is $150,000. So for the lower payment, you can calculate the each month. Well, no, you don't even have to do that. You just have to take the total amount you paid and subtract the value of the house, which is $150,000, and that gives you the amount of interest you paid. So we take $396,234, subtract the price of the house initially. In the first case, you paid $246,234 in mortgage in interest. So $150,000 in principal. This in interest gives you the total amount you paid. Whereas in the second case, $1,254.68, you have $301,123 minus $150,000. 301,123 minus 150,000 gives you $151,123. So you can see the amount of interest you pay is even more significant. The difference is. And it says, what is the vertical asymptote for the model? So the vertical asymptote is x equals the is your monthly part of the amount your monthly payment is paying towards the principal. So what you do is you take 150,000, divide by 12, and divide by 1,000. Well, actually, we don't even have to do that because it says that so what is the vertical asymptote for the model? Well, simply said, it's x equals 1,000. And that, if you go back to the original equation, you'll see that's when this goes to 0. And this goes to 0. I mean, this goes, if you let x go to 1,000, then you get 1,000 divided by 0, which is infinity, which you can't. So you can't have a value less than 1,000. Actually, there's another part of the curve. I think you could have graded mathematically. You could have some negative number, but 1,000, I think, is what you would pay if your interest rate, if you're just paying the interest on the loan. I think that's what that is. Then you'd have to pay forever. So if we take, so yeah, that's what we're going to do is if we take $150,000 and you divide by 12, that's going to tell you no, let's make sure I do this right here. So so take $150,000 and you multiply by the interest rate, and then you divide by, so that's your interest per year, and then you divide by 12 months. That tells you how much you'd pay in interest every month if you were just paying the interest and you weren't paying any of the balance off. So if you take 150,000 times 0.08 and you divide by 12, you should get 1,000. Okay, so that's where the 1,000 comes from, and that's what the context is, the meaning. If you pay less than 1,000, your balance would continue to get more. You're trying to reduce your balance, but if you wanted to just pay off enough to pay the interest on the loan, and there used to be loans called interest-only loans, and the whole idea there was you didn't plan on living in the house forever, and you were hoping that the value of the house would go up, so you were just kind of holding on to the property until the value could increase, and then you could sell it and then make a profit. That was kind of when the housing prices were really increasing rapidly.